State?
statue.
Statue?
Statue. Seasonal protection. Most of them member.
In your contact.
Also go you should study from Mexico.
Satu sensei said to him, who study Excel? Just use.
No, I also don't know how to teach. Just accept. And it's just equation, it's just a graph.
Easy. I have one question. Like, for example, you know that Chong Sensei, Chong Sensei published one paper for my research, right? And it's in Australia. So, is that can be count as my
No.
pick? Because why?
Because the topic is different. If the topic is related to your PhD study, it will be counted.
Okay.
But I heard if we publish more than four, then we can finish earlier.
Huh? Oh,
I didn't know.
wow. So you already finished
No,
4?
not yet. I need one,
Gawati?
but I don't want to finish early.
Huh?
I don't want to finish early.
Oh, and later you don't have scholarship, right?
I should use.
Take everything.
Yeah.
Oh, me too. Sensei, are you joining the meeting today?
I want to do. Will you ask about the symposium?
Yes. Maybe at the end of the meeting, maybe?
Mhm.
Hmm.
投稿するところはそこでいいですか？
Hello, Sensei. I can share something. Can you see my screen, Sensei? Okay. Okay. So I found one paper about how from the system we can estimate rotation demand in high-rise stories. In this paper, they have two different heights. One is medium 10 story, and then another one is 20 story. So from the mechanism, the objective of this paper is to simplify procedure for estimating maximum inelastic wall rotation and the maximum coupling being caught. Means it find a simplified equation to relate the rotation of the wall and also the rotation of the coupling beam. And here we have elastic displacement and also inelastic displacement. And for elastic displacement, the rotation is considered from the total height of the wall. Meanwhile, for inelastic, is considered from the plastic hinge, which is here. Yes, there's a difference between these two. So they have two objectives. First is considering about the shear wall, and another one is considering about the coupling beam. So the first one uh, is to identify the simple relationship between inelastic relation demand and the total displacement demand. Because if we can see here, the total displacement is considering inelastic and elastic. And the issue is the variation in displacement at the maximum H rotation as a ratio of maximum displacement, and secondly, the variation of elastic portion of the displacement. The solution in this paper is to combine these two problems to develop a concept of equivalent elastic displacement that is different between maximum total displacement and elastic displacement corresponding to the maximum rotation. And how we estimate the elastic drift. So the first approach is to assume the difference between maximum top displacement and the elastic top wall displacement at the same of maximum base rotation is equal to the first mode of yield displacement. So they use this equation to estimate the displacement. And if you can see here, the black dot is for the cantilever and the white dot is for the couple. So in this experiment, they have two different wall. They have couple wall and they also have only cantilever wall. So that's why they have two different type. Uh, this side, this side wall. Yes, sensei. Mm. So we can see the distribution here, and the for this first approach, by using this formula, is only good for short cantilever wall, but it's not recommended for couple wall because they have different mechanism. And then the second approach is to assume in elastic drift, the displacement in elastic displacement divided by the total height after the plastic hinge, which is equal to inelastic rotation of the wall, is equal to the maximum global drift, delta max over delta W, the total height of the wall. So by using this equation, estimate of inelastic rotation, delta I equal to the displacement elastic divided by the height of after plastic hinge, also equal to the total displacement of the wall and divide by the total height of the wall. Yeah, for and they also have two different the is elastic displacement for cantilever wall and the couple wall. The result is very conservative for the cantilever wall, but is very good result for estimating the couple wall. This is for non-elastic displacement. This is by using equation 5 and 6. And then they have a third approach. The third approach they doesn't use any equation, but he used the store the elastic displacement of the wall. So basically, it used the maximum mid-height displacement and an estimation of equivalent elastic at the mid-height of displacement. So they considering the elastic displacement at the mid-height of the wall. So this the first photo is for 10-story height, and the second one is for 20-story height. And then the second objective, they discuss about coupling beam. So in coupling beam, develop a simple relationship between the rotational demand of coupling beam and the total displacement demand. So the idea is the critical wall slope is approximately equal to the maximum global drift, and the critical floor slope is very small compared to the critical wall slope. So the suggestion is the maximum coupling beam rotation might be proportional to the maximum global drifts, as it depends on the critical wall and critical flow. So this figure will this the I will explain later about the this sentence in this photo. But here the displacement profile are normalized by the maximum top displacement. It means for the 10-story and 20-story is different because the mechanism of as height increase the mechanism of the wall change. So for the short wall for like a 10-story, the top story can be equal to the max total displacement, which is the rotation of the coupling beam is the maximum. We can see in the figure 1 it's a straight line, and we compare to the higher story for the 20-story building, the it tends to bend in the middle of the story in effect of a higher mode mechanism for this building. So for the long wall, the top story cannot be considered as maximum displacement, and also cannot be considered as maximum rotation for the coupling beam. The critical level means the wall slope and the is combined with the floor slope, which also explained in this figure. If you can see this, the black line is the rotation for the coupling beam, and the blue one is the wall slope, and the red one is the floor slope. And this is the first one is for the short story height, and the second is for the 20-story height building. And we can see the 10-story height, the rotation is not much different compared to the 20-story height. If you can see the top displacement of the 20-story height, it goes to 0. The normalized rotation become to 0 compared to the 10-story height. And the critical level is the maximum slope of wall and combined to the maximum slope of the floor. If you can see here, is the maximum slope of the wall, and for not for the floor slope, but the critical level will be here, is the maximum rotation of the coupling beam. And the critical level is also known as the global drift, and the wall slope is the largest at the bottom and the decrease near to the top due to coupling being pulled back, and also a higher mode for the taller wall. And the rotation of coupling beam maximum, where maximum slope, wall slope minus the floor slope, like here. So it is the maximum for the coupling beam rotation. So at the top level, the wall slope is equal to the floor slope and equal to the coupling beam. rotation is small. But this concept is only considered when the degree of coupling is less than 70%. And from this concept, they estimate how the coupling being one rotation by this maximum displacement is the displacement demand of the wall calculated by the linear dynamic analysis, whereas the rotational of couple B equal to maximum displacement divided by total height and times the ratio of total length of the center wall divided by the length of the coupling beam. So, in for this concept in this paper, they only estimated for the coupling beam itself, but it doesn't estimate for coupling beam including uh, damper. So maybe the mechanism will be different from yours. This is from your suggestion. When we have the damper in the middle, we can also estimate the rotation of the coupling beam, and maybe we can find some equation to estimate a coupling wall with damper in future. And I have one question from here. We only estimate from the half of the wall, right? But if do when we consider a coupling wall, do we have to consider four poles wall? This is from a book, Priestley. It's not Priestley book. It's a from Pauli book. And from here, this equation is combined between two wall system. So from the left and also from the right, if you can see equation 10.11, so we have the external moment from the external energy. We minus the moment of the first wall, and for the second wall, it's only have moment from the wall itself. So maybe this also we have to consider when we do a dynamic analysis. Hmm. Reinforced concrete since yielding happen based on it's depend on the type of building, short story building or high rise building. So for flexure sensing, flexure, yes. Mm. And let me show you the paper here. Uh, mm-hmm. So I think it doesn't show the arrangement of the coupling beam, but vertical building. It looks like a normal coupling beam. It doesn't say diagonal coupling beam. Only this. There's no more. Only the section of the building. But it mentioned that the degree of coupling less than 70%. So uh, if we use diagonal coupling ring, it's almost 66%. Uh, this estimate the displacement. So for the wall, they have three approach, but the most for it's depend on which kind of wall that we want to consider. Is it couple wall or only cantilever wall? So for the cantilever wall, we can use these equations. And but for the if we use consider for couple wall, we should consider this one, these equations. Hmm. So the rotational, they consider the is inelastic drift and also inelastic rotational theta I r here. Remember, mm, mm, I believe r is I read about r, but I forgot about the r. It's related to the um, rush shouldn't. Hmm. Mm. Yes, this one. Mm-hmm. R base of structure. Mm. This one. Mm. 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 This was elastic demand. Elastic. Mm-hmm. 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 Mm. Mm. This works. Mm. Elastic demand to strength. Mm. I understand. Okay. Uh, rotation at the mm, the flow slope at here. Here's instead flow slope. And the wall slope here. Mm. It's not based on theoretical. Mm. Understand. Mm. If we want to try for a higher story also, it will not be accurate for our research. That's what you mean. Mm. Mm. Yes, understand. It's just based on the experimental result. Mm. Okay, so yes, sensei. Mm-hmm. This one. Uh, yes. It's just mm, mm-hmm, mm, mm, yes. Okay. It's the 10.11. We can only use one. Mm, yes, yes, yes. Mm-mm. Yes. Mm, mm, yes. Yes. Mm-mm. Mm, mm, yes. Mm, mm-hmm, mm-hmm. Yes, yes, yes. Mm, mm, mm-hmm, mm-hmm, mm-hmm. Okay. Yes, yes. Mm, so that's it. I will open the book. So that's it. Mm. Yes, 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 they have explanation. Excuse me. Uh, here, this is a book from a tall building. So, so here we can see wall, wall one and wall two, and they get this equation when wall one plus wall two, and then after that they double integrate, and they get this formula, and then there's a lot of equation, and then finally try to find this endpoint that it mm. uh tall with I will show you tall breathing. Yes, 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 yes. Mm, mm. This one 13. Mm. Let me open the book. Mm. I think this is page 227. It's years ago. Mm. Mm. I think I put in the Google Drive since it. Check. Hmm. I, ah, since it, if you open the our Google Drive, you just type tall and you can find the this one. So this is this is our Google Drive, like Google Drive, and you just type tall, and this the first one. So this is the book. Mm. Okay. Yes. Yes. Mm. Mm. Mm-hmm. Mm. Okay, Sensei. Yeah, mm, mm. I I think I remember that the equations Sensei, they actually was study about the parameter of KAH, and it also related to degree of coupling. For this book, they doesn't use degree of coupling, but they use this one, a parameter of KAH. Yeah, it's one of approach without using degree of coupling. K, uh, H is the height of the building. A is how can I say? I think K also come from here. A simplified stiffness parameter is regard K is stiffness, and A is like how can I say? A coefficient. Mm. So they have done a lot of analysis, and they simplified to a simple formula like this. Mm. Like they have many trial like this, and they simplified the formula like this. Yes. Mm-hmm. Do you want to share your screen, Sensei? Mm. 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 Yes. Mm. Yes. Like it. Mm-hmm. 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 Yes. Yes. Mm. 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 Mm-hmm. Mm-hmm. Yes. Yes. We have in the beginning we have 0%, 5%, 2%, 5%, 10%, 25, 57, and then 75, and then we simplify to only four. Yeah. Mm. This year, that's right. Yes. 400. 400. No, 400. Mm. Yes. The Q. Mm-hmm. Mm. 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 Um, yes. Mm. Yes, yes. Mm. Yes. Mm. Yes. Good question. Yes. It's long formula. Let me check. Right. Yes, yes, yes. Sheer wall. Wall. The first one. 17A. Yeah. The wall building. Yes. And then the coupling for the coupling beam, we use the h equal to 2 over pi times 1 minus 1. Yes. Yes, there's one PDF file that you gave to me, Sensei. Do you remember 0.8h? The 0.8. Mm. Yes, yes. Mm. Mm. Yes. Energy. Mm. Mm. Mm-hmm. Yes. Yes. Mm. Yes. Mm. Yes. Yes. Oh, yes, yes. Yes. Okay. Okay. Let me share. Okay. So we have the result here. Mm-hmm. Actually, sensei is not conversion. It's actually the blue line have to be lower than the red line. So if you can see the story drift here, so if you can see the story drift here for 120 second random phase, the 10% damper it touched the maximum drift. For Kobe, the one that touched the maximum over the maximum drift is the blue line, which is the 10%. And yeah, mm, okay, mm-hmm. Yes, 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 see, yes, yes, mm, yes, sensei. Um, but if we can see El Centro, sensei, 75 at the bottom story, it exceeded the limit drift. So the most considerable design is 50%. If you can see El Centro and Kobe, like uh, it doesn't exceed much compared to the maximum drift. Yeah. Yes. Yeah. X. Yes. So I think the how much different between the red line and the blue line is also consider the performance of the structure. If you can see 25 and 75, the distance between blue line and the red line is quite close compared to 50%. Yes. Going down, but for yes. But sensei, if you can see here, uh, this one is 2, right? This is 2, and this one, yeah, is increasing, like become to 3%. But the capacity, the one that we, the capacity is increasing, but the blue line is changing. The yeah, the blue line is depends on the effective periods that we calculate. Mm. Yes, I think we missed something in the middle. Mm-hmm. Yes. Mm-hmm. estimation. Okay. Yes. Mhm. Mm. Right. Mm-hmm. Okay. Mm. Mm. Mm-hmm. Yes. Mm-hmm. Mm-hmm.
Hi.
Mm-hmm. Mm-hmm. Mm. Mm-hmm. Mm-hmm. Mm. Mm-hmm. 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 Mm. Okay. Okay. Mm. Mm. Sensei, I have one question. If we use visco damper, we put the damper in the middle, or it should be diagonal directions? Do you mean the viscose damper or viscoelastic damper? Yeah. Okay. Yes, sensei. Okay. Viscoelastic damper. Okay. Uh huh. Yes. 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 Mm. Yes, sensei. Mm. I believe so. I will check later, sensei. I will share with you. Mm. Mm. Mm-hmm. Yes. Okay. Accurate. Okay, sensei. Each other sensei. Mm. Mm-hmm. Mm. Sensei, can I have one question? Uh, how we can, for the university requirement, how do we know that the symposium is considerable as one of the requirement? Mm-hmm. 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 Ah, okay. Mm. 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 I see. Mm-hmm. Mm. Mm-hmm. Mm-hmm. Okay, sensei. Thank you so much, sensei.
For the application of extend driving license, they started they opened the form at 7 a.m. but still the form is open, not finished yet.
7 p.m.
At
7.
7 a.m. It's open 7 a.m. but still it's open.
Really?
Yeah, this one. To send one driver license possible. Still,
This is for 27.
yeah, 27.
Wow. Mm. Mm, 27. For Monday.
And with this, no code.
20.
28.
Oh, okay. 27 is for invitation.
Thursday.
Where is that? Maybe they are open.
Mm.
And look at this. I think there's a spring sensei here. If you can see the B, figure B, there is a spring in between the roller. This there's a spring between the damper. There's a spring connected to the the spring no, at the side on both sides they have spring holding the damper. Can you see? No, sensei. Uh, yes, sensei. The red, the one that you draw. That's a spring, I think. Yes. Mm.
はい。あ、誰ですか？あ、でも埼玉県のところです。はい。
誰？
知らない。
I'm okay, Sensei. I'm okay, Sensei. Sensei? Sensei, Sensei, I just want to say I put the paper on his folder.
I sent email.
Yeah, I sent email. So funny. My computer stuck and then suddenly disappear.